Okay, let's get started. Okay, so dim that. Okay, so the decay rate is not too bad yet. Okay, so welcome back. Today we will start the real lecture. So the Tuesday we have some warm up on all the things about Python that you might want to know, and today we started to go to the lecture. Just in case you miss last Tuesday lecture, so there are some logistic. I think the main thing here is that the office hour will be held like after the lecture on both Tuesday and Thursday. In fact, I also just talked to the tutor. He's also quite kind to extend the office hour. So if you have things that that cannot be resolved and need to have more one-to-one tutoring, he will be available from 3 to 3:30. I still haven't heard back from him on where to meet, but that will be the office hours. Of course, you are always feel free to reach out to me by emails. And okay, so the plan for today is is technically the first lecture of the second half. So the first part we will give sort of some understanding of some of the jargon that we will be using throughout the courses in machine learning. So what do we mean by supervised learning and supervised learning? Of course, for any machine learning courses, then we need to understand how to cross up or validate your models. How do you choose the best models? And then we will start to talk about the statistic part, right? So I think one of the misconception about machine learning is a black box, but it's quite far from the black box, right? So the key idea of machine learning quite often can be regarded as the extension of statistic. And in terms of astronomy, the only statistic that quite often we do is just the Bayesian statistic. So we will explain why this is the case. And I thought I will start by the Bayesian statistic because this gives you the framework to understand all the lecture in this next 6 weeks. Because quite often I think we treat individual machine learning as individual tools, but all of this can be understood in the framework of a Bayesian inference. And even for things as simple as we will discuss today, like the linear regression, most of the things that we want to understand about the linear regression can also be understood through the lens of Bayesian inference. So I should warn that, of course, it's quite a steep learning curve because we go straight into the Bayesian statistic. And if you are not familiar with the idea of the Bayesian statistic, it might get some time to use to, but once you get used to the idea, you will sort of have a more helicopter view of all the things that we will discuss today. I should also mention that the linear regression might be the most important thing that you can learn for jobs, because 80% of the jobs, or probably more, in industry are just done with a linear regression. So if you learn this courses like this lecture well, then you can do about 80% of the data science job that is out there. You will see why. There's no shame. I was having a dinner with my friends who is now working in a big company in Australia that I shouldn't name where, but he just my day job is I walk into the company, I just do a linear regression day by day and make a lot of money. That is kind of true. So you will see that you will be surprised, even for as simple thing as the linear regression can be quite mathematically beautiful, which is what we try to cover today. And because we say we will walk through the models through the lens of a Bayesian inference, so we will talk about where does it come from, things that we use daily, like chi-square minimization. So how should you understand chi-square minimization? And from that, we extend to the Bayesian linear regression and walk into some of the topic that you might have heard of in your research, like the regularization of the models. How should we like derive that from more or less first principle through the lens of Bayes inference. So that's the plan for today. There are really not many prerequisites for the courses, but of course, a good understanding of the probability and linear algebra will be quite helpful. It's really not, strictly speaking, a prerequisite because we are only using bits and pieces of statistics and linear algebra, meaning that even you are not familiar with some of this like concept, you can either talk to me, or you can find some good resources that online that will, like probably a YouTube video or two should help you to clarify some of the idea that we might need in these courses. Python, as I mentioned, is quite useful. So it's meant to be a heavy on problem solving skill. So understanding well Python is quite essential. So as I mentioned on Tuesday, you probably do not need any textbook for the second half because most of the lectures should be self-contained. That said, of course, we are still assuming you have some understanding on some of the concepts in probability and linear algebra. If that turned out to be a bit tricky, say for the math on the probability and linear algebra, I would recommend the book on the left. So this is sort of an introductory book for machine learning. It's also the inside joke is that we rebrand the book as the mathematics for machine learning, but under the hood it's just a linear algebra. So if you say you teach linear algebra, like nobody will come to the courses. But if you teach mathematics for machine learning, then you sell books. All right. But of course, that is a very basic books, and most of the lecture that we will cover today is also quite a simpler version to say Comp 46 or 70. So the textbook on the right is a very good textbook that we use for Comp 46 or 70, which is, if you want to get in-depth understanding of machine learning, I would recommend you to go through the textbook end to end. So it's a very timeless textbook. It's not easy. So I used to be meant to be first year PhD student in com science, but it covers basically all the key idea in what we call a classical machine learning, which is a big part of things that we will cover in this lecture. I really like to liken machine learning like pop songs, right? So it's like music, right? So most of the things that we will be learning in this lecture is quite straightforward, what we call classical machine learning. And you might say, well, why do I need to know that? Just like, I love K-pop, right? Do I need to know about classical music? Yes, because you might actually learn that even K-pop has a lot of thoughts inside K-pop. It's just not like a random note string together. So if you can understand the classical music, then you can get a better appreciation even in your daily life. You use more modern too, which is also the gist of the lecture. You will see even for today, you will see the math just it's very steep, but it's also meant to, if you understand a very good background in classical music, not only you can play well the classical symphony like Bach or Beethoven, but you can also start to appreciate more some of the more moderns too. So what is machine learning? So I think this term is kind of being misused a lot, right? So seems like everyone is doing a machine learning nowadays and not. But it's also technically true, because the definition of machine learning is just try to understand how we can program something without explicitly doing that. So what do I mean by that, right? So if you learn your Python 101, then you might have learned, the first thing you learn is if-else clause. And this is a very explicit programming, meaning that if I see the input X, I will output some value Y. If I see the other input X, I will output another like a value y. So this is classical, very explicit like programming. But what the machine learning try to do is to say, can I not explicitly say what the input might be, but rather I try to build a models to understand the underlying data that I have. This might seem a bit like high level, but like as we go to a more specific example, hopefully this will become clearer. And this is also why the machine learning is particularly important for astronomy, because in many cases, what we try to do in astronomy is try to build an understanding of a worldview based on the data that we have. Ideally, of course, you say, I want to do something from first principle. So that is called the pure modeling. Think about a classical modeling will be the orbits of a binary star, right? So you know exactly how the star should orbit. So you fit a models based on the physical understanding of the system. But in many cases, we simply like do not know all the first principle like models, right? If we know that, then we would not need to do the research in the first place. Quite often, what we try to do is to say, we have only the realization of the universe, and we try to build an understanding of the cosmos like around us. And this is the learning part. So in a not very a rigorous term, you can think about learning is giving more flexibility to the models, and the modeling is giving more like rigidity to the models. And one misconception is like, is either machine learning or not, but actually no, right? So anything that we do in research is between learning and modeling. So take the example of what we will learn like today. We will fit a line, a linear, a regression. That is a learning part, but there's also the modeling part. And the modeling part is that we're making the assumption the underlying data follows some hyperplane. And this always happens in machine learning. Most of the thing that we are doing in machine learning, we are making some assumption on the data. We're assuming that the data is not completely like random. It's just how much what we call inductive biases that we need to include in the model so that you can gain insights from that. So for most of the things that we do, you try not to do the machine learning, because if you give full freedom, you learn like nothing. But sometimes you need to like give more freedom in order to understand the system at hand. So as we step through more example, hopefully this will become clear, like clearer what do I mean. Like keep in mind, that there's no such thing as I am doing machine learning, you are not, and you are not also doing like physical modeling. It's always somewhere in between. So in terms of machine learning, there are basically three main regime: the supervised learning, the unsupervised learning, and reinforcement learning. We will not talk about reinforcement learning, unfortunately, because reinforcement learning is also turned out to be the hardest one. That's also sort of the path toward what we call the AGI, the artificial general intelligence. But for good reason, because most of the things that we care about in astronomy actually have not been applied. Like technique in reinforcement learning seldom applied to astronomy. So most of the things that we care about is mostly in the regime of supervised and unsupervised. I will tell you what that means. So take the example of how should you understand supervised and unsupervised. A good example will be understanding the real estate in Canberra, which is horrendous, if you know. So you have some real estate and you try to understand the landscape of the real estate. If you want to understand the landscape of real estate, there are quite a few questions that you could ask. So one simple task to build a worldview of the real estate is by doing some supervised tasks, meaning that I have some input like feature X, and I have some output like feature Y. So I separate what I want to input and what I want to output. So take X as the square feet, so the area of the houses, and Y to be the price of the houses. And you can build a worldview because you know that the prices of your houses is not random. I hope they are like random, but they are not, right? So there is a relation between the input and the output. If you can understand the relation between the input and the output, you start to understand the real estate system like better. So the supervised task say I have some target like output Y that I try to predict that with X. You might say, well, of course, like if you have X and Y, you can feed a data. So like the supervised learning, in many cases, it's just like feeding a line to the data, right? And of course, this is a very like simplistic view. In principle, both your input and output can be multi-dimensional. So you can have multiple input to predict one output and vice versa. So you can have a vector input and a vector output, which is what we will cover today. You might ask, why is this important for astronomy? So sometimes just understanding there is a relation between X and Y tell you something about the underlying system, right? So a good example will be the M sigma relation. So what the M sigma relation say is that there is a relation between the black hole mass in the y-axis with the galaxy mass, in particular the central bulge mass. And people have long seen that there is a strong relation between these two things. This has two implications. The more shallow one is great, right? Because it's very hard to measure the mass of the central mass black hole, but it's much easier to measure the mass of the galaxy or the bulge. And it's called M sigma because most of the central bulge come from the velocity dispersion of the stars. So if you can measure X, you can infer Y. This is very handy because in many cases, it's very expensive to measure Y. And if you have a strong worldview about how things are connected, then you can start to make inferences on things that are hard to measure. But actually go more profound than that. The relation puzzle many people even until now for many decades, because you would not expect this relation to exist because the black hole is very, very small at the center of the galaxy. So you have some gravity pull on the stars that are around the galaxy. So a priori, you would not expect the galaxy mass should know something about the black hole and vice versa. How would something in the middle, is like you standing here, but you are controlling the whole size of the camera, right? How can that happen? And because of that relation, the people start to build insights into how the galaxy was hierarchically built and how the black hole was filled. So that's beyond the topic of this lecture, but this tells you that even for supervised tasks, understanding that exists a relation between X and Y sometimes is quite informative. And in terms of the supervised learning, of course, there are two different tasks. One is the regression task, and one is the classification task. So the regression task, it just means that your output is a continuous variable, like the price of the houses or the black hole mass. So you can take any value in a continuous domain. But quite often, in many tasks in astronomy, we care more than just the regression task. Sometimes we want to do the classification. So the classification just means that your label, your target Y, is a discrete variable into different classes, like man, woman, cat, dogs, right? So these are different classes. Next, like you might think, well, why not just treat the discrete variable also as a regression task? The next lecture, we will talk about why this cannot be regarded exactly the same thing, because there are some pathology that you need to avoid. And what is the classification task? It's just if I have, say, two properties, the size of the houses and the lot sizes. If I now see that there are two different trends, so my goal is to try to find the boundary condition that can separate class A from class B. And this happens a lot more often than you taught in astronomy. A great example will be the star galaxy separation. So for many observations that you do, quite often you need to select the sources, and selecting sources quite often comes down to a classification task. because what you have on the sky is a projected view of the sky. So a priori, we do not know if this is a star or this is a galaxy. In fact, it takes us a long time until we know that we are not the only like galaxy. And this has a practical like implication. Think about if I want to do a survey of galaxy, right? How to optimize the selection of the galaxy. Of course, if you have infinite observations, say I take the spectra from the object, then it would be quite easy to know if something is a star or a galaxy. But the task is that if you have like a limited observation, can you still do that efficiently? And this is also one of the main like application from the Gaia data, because for the longest time, people cannot like differentiate if something is a high redshift like galaxy. They actually write a Nature paper, or a nearby like M dwarf star that no one care. Someone care, not lots of people. Because of Gaia, you have more features. Now you have the motion of things. Then you can like separate the star from the galaxy. Right. So there's one task. So that's sort of the unsupervised, the supervised task, the regression and the classification. There's also like the other like domain in machine learning. It's called the unsupervised learning. It's just a fancy term to say, what if I do not want to separate X and Y? So I do not want to define something as input and something as output. I just have a bunch of features X. So if I use boldface, like it means a vector or a tensor. And I want to find some interesting trend within the data. And this is, of course, quite, if you look at these two examples, like you can see the differences between the supervised task and the unsupervised task. So supervised task, you already know there are some classes. For the unsupervised task, you do not make that assumption. You just say, well, can I find some trend within the data, right? So if you squint your eye, you can say, can I say there are 3 clusters, or can I say there are 2 trends? And both of these are interesting things, because quite often in astronomy, we want to find objects or trends that we did not know. So for unsupervised learning, it comes down to 2 main like topics. One is dimension reduction, and the other is clustering. So the clustering is trying to try to find like cluster, but you can only find good cluster if you can compress information, right? So if you are living in a very high dimensional space, it's very hard to do the clustering. And many observations in astronomy are very high dimensional. So take the example of spectra. The spectra could have n pixel. Pixel can be thousands or tens of thousands of pixels. Then to do clustering in that space is very tough. So the first task that you want to do is to compress the information to a regime that you can do like clustering or do like a regression. And this is also the question tree in assignment tree. We'll cover 2 basic techniques. So for clustering and dimension reduction. And you shouldn't underestimate it, despite this is sort of introductory courses to machine learning. It can really solve a large part of the problem in astronomy. So why unsupervised learning is interesting. So for example here, this is a famous paper now. I think it's cited like 200 times in like few years. So people are looking at the energy of the orbits of the star, like versus some angular momentums. And if you plot the correct feature, then you can start to see a lot of trend and clustering. To be fair, because I'm on the paper, I know what this is done. So like there's no machine learning. People are just like, oh no, I just make some cut, I see some trend, which is fine. That's the human like clustering. There are more than that, but even that, you see that, well, there are lots of things. If you squint your eye, you can see this thing. It turns out to be real. So you can follow up and show that this separation of data in some space tell you about different small galaxies that merge with the Milky Way. So individual parts here are the different parts of the galaxy that have merged with the Milky Way and form the Milky Way today. So being able to find clustering is important. On dimension reduction, this is a very shameless thing. It's funny, actually, this is done here before I did my PhD. So this is actually my first paper with Ken Freeman. Turned out to also be one of my most cited paper, right? So this is cited, I think, like 130 to 150 times now. And you might say this is a super dumb because I'm applying PCA, which is five lines of code, to a 25 dimensional space with 200 stars, because we don't even have like Gala then. This is a very old in 2012. But even simple data, building insights from that can lead to quite some understanding of the system. Right? So we will talk about that a little bit more. But even PCA has been used in many cases. So in the assignment 3, the question 3, you will look at how to use PCA to understand the quasar spectra, because you know that most of the quasar is just the accreting black hole, and the spectra looks like the red line here. And even though there seems to have like many pixels, you know that there are only finite mechanism that is feeding the black hole, right? So therefore, if you can compress the information from n pixel to small numbers of components, then you can start to understand the accretion of the black hole, like, which is what you will try to do in your assignment. And still, right, like despite this is very simple, it still go pretty far. So even this is very simple idea. If you have a good understanding on the mathematics behind, so this is a paper actually published this year. It was written last year. We are just extending the PCA to something slightly more advanced and more like general. This also speaks to, you shouldn't just treat all the two as two lines of things in your sklearn, because once you know the mathematics behind, then you know what you can extend that for. And a lot of interesting research is done when you know the math and know what is the limitation, and try to build some finite extension on works that people have done. So the helicopter view of the second half. So the first part is what I call the basic. We will starting with the supervised learning. So a lecture on the regression today, a lecture on the classification next Tuesday, and then we'll go to unsupervised learning to talk about clustering and dimension reduction. This 4 lecture will give you a flavor of all these very different tasks that we care about in astronomy. But of course, this is sort of the absolute basic of tools that you can have for machine learning. And then we go into something slightly more fun, which is a neural network. As I mentioned, machine learning in astronomy has a very interesting reputation, because I feel like people either idolize it too much or scoff at it too much, right? So machine learning, the concept of machine learning is absolutely not new. It comes before the computers, right? So if you think about where the machine learnings come from, when Turing write his paper before we have computer, he started to ask, can the machine learn? That's I think the first or second sentence in his paper. That's the beginning of machine learning. But it became a very trendy word, not because of the machine learning terms, but rather a subset of machine learning that is based on the idea of a neural network that tend to work pretty well. So we go through some of some concepts. So this is this is the basic do re mi fa sol of machine learning, and then we go to a K-pop just to give you a little bit of sense of K-pops, right? And we will go through the supervised and unsupervised learning. It does not mean that you can understand all the magic in the K-pops, but it's good to listen to that once. And then once you can get a sense of why the K-pop is attracting, then we go back to study the classical music. So the pinnacle of classical music in classical machine learning is called the Gaussian process, because of the Bach or the Beethoven of the machine learning, right? So we'll go through that, but all this is all through the lens of Bayesian inference. And then if you look things through the lens of Bayesian inference, then you will start to see the needs to do some sampling of posterior estimate, starting from today. In some cases, you can get the posterior quite easily, but sometimes you cannot, which is where the sampling comes in. And finally, even though this second half is fast enough, I still try to squeeze out a lecture to talk about the large language models, because I think that is quite important to understand what you can do with them more than just prompting your chat GPT, right? So there are a lot more you can do. So I hope to give you some overview what is behind the scene for, say, ChatGPT and how you can fine-tune the models. Okay, so that's the helicopter view, but let's come back a little bit on the machine learning. So we will be starting with supervised learning, right? For any machine learning, we need to answer the question, how do I know my machine learning is working? What do you constitute a good fit? And to understand, like, to intuitively understand that, one can start with a simple example. So let's say I have a data Y that I want to infer with input X. I can build a very simple models, like a polynomial fitting. Then the question is like, how many order of a polynomial I should use? Clearly, right, if I have the data in yellow, if I use too little, very rigid models, then I will underfit the data. If I use the right amount, that's good. If I use too many freedom, then I will overfit the data, right? And this is also what I meant by a good push and pull from learning and modeling. For most of the things that you care about, you want to understand the balance between the learning and the modeling part. But how do you quantify what is a good fit and what is a bad fit? So the simplest thing you could do is to do what we call a cross validation, meaning that a fair test to see how good the model is. So classically, what this means is that you set apart some of the data to be the testing set that is not used in the fitting, right? So a simpler way, so like there's no absolutely truth to do that. The simplest thing is to just break things, in like 60, 40, or like 80, like the 20 between the training and testing. So you use the training data to fit the models and have some metric on how good the fit is, how good the prediction is, comparing the training and the testing. Just like in the polynomial case, you would expect for the training data, if I increase the degree of freedoms, I will keep improving my fits. But at some point, even though I am improving my fits, the performance on the data that I have not used in my fitting will be worse because I am over fitting. So from this, you can start to determine what would be a good models. But there's a catch here. If I just use a training and testing, there's a slight logical flaw because I am still using my test data to determine the best order of a polynomial that I am using. In practice, this does not matter too much, especially in astronomy. We have very limited training data. But if you want to do things exactly correctly, so you want to make sure that the true test data set is not even influencing the choice of the hyperparameter that I set. So this is why quite often you need to break into training, validation, and testing. So the training will be the data that you use to fit the polynomial. The validation set will be the one that you check the trend of what we call the loss function here to set the best models. And finally, also further test that on the test set that has no roles in any way in all the training and the decision. I pause here. Do people have any question? See people online. No question. Where's my cursor? I cannot see my cursor. What's going on? Oh shit! Did I break something? Okay. Do that again. Oh, why can I not? Okay, sorry about that. Technical failure. Okay, so as I mentioned, I really want to start the courses because it's a very compact courses. I want to start with solve the right framework. So most of the things that we will talk about will be in the context of Bayesian statistic. And of course, to understand the Bayesian statistic, you need to know what is statistic. And the statistic, of course, is a study of probability. Right? So hopefully you have learned this all in your high school or in the first few years of your college. But like even you have not learned that, that's fine, because the only things that we need to know for these like courses is the sum rule and the products rule. So the sum rule say, let's say I have two random the variable x and y, the marginal distribution of a distribution just integrating over the other. So the easiest way to understand this is, let's say x is the chances that I bring an umbrella and y is the chances that it rains. If I want to ask what is the chances that I bring an umbrella today, irrespective of it rains or not, is equals to the probability of me bring an umbrella and it rains plus me bring an umbrella that it does not rain, right? So I marginalize over all the cases where it rains like or not, so that will give me my probability of me bringing an umbrella. But more importantly for Bayesian statistic is the idea of the products rule, meaning that if I want to ask what's the chances that I bring an umbrella and it rains, it will equals to the chances that it rains plus it rains and then I bring an umbrella, right? So this notation means conditional distribution. And if I skip one of the index, it just means that it's a marginal distribution. So I hope like this is clear. If for any student that have like problems to follow the probability, it's good to make sure that you get this right. I'm happy to talk to you in person if this is not clear. Why the product rule is interesting? Because just by writing down px given y, px and y is equals to px given y times py, a priori, like there is no reason why you should first know y and then like calculate x. You can swap the order. You can say the chances that I bring an umbrella and it rains equals to the chances that I bring an umbrella times the probability that I bring an umbrella and it rains, right? Why this is important? Because if you have two variables, then you can swap the order. You will get px given y equals to py given x times px divided by py. So keep this in mind. We'll come back in 2 slides to say why this seemingly a high school equation is very profound in a statistic. So this leads us to this dude. Who is this dude? So this dude is Thomas Bayes, who is the base of inference, right? So as I mentioned, in astronomy, you almost always do the Bayesian inference. I'm often very amused when people write paper and say, we do Bayesian statistic. I'm like, what else would you do? The astronomy, you would only do the Bayesian statistic in many, many cases. But to understand what is the concept of like Bayesian statistic, then you need to understand what is the differences between the frequentist approach. So the frequentist approach is very easy to understand. So as the name suggests, how do I know, say, a dice is fair? So the frequentist approach say, if I want to understand if a dice is fair or not, the best way I can do is to repeat the experiment many, many times. If I roll the dice many, many times and I plot the histogram, the output, if it forms a uniform histogram, then I say the dice is fair. This is very logical, provided that we can repeat the experiment. Guess what? We cannot repeat the experiment? The universe, right? We only have one universe. We have only one Milky Way. Too bad for you. You cannot roll the dice many times. And this actually is the thought experiment that Bayes do. They ask the question, what happened? Can we still understand the truth that we live in if I cannot repeat the experiment? This is a very fundamental question that the human race face. And the concept of Bayes say is, yes, you can still understand the truth as long as you can admit the fact that because our observation is finite, and therefore our understanding of the universe is imperfect. Meaning that whatever you do, you will never know exactly the truth. So if you treat the models like a WU as the model itself should also be uncertain. This is profound because this means that you put the data and your models on the same like footing. So they are both random variable. One is not more novel than the other. And it's important to mention that like this does not mean that Bayes do not believe there is the truth of the universe. It does not mean that it does not believe that there is one numbers about dark energy that govern the universe. Just that because we live in one of the universe, we have one realization that it's impossible for us to be absolutely clear. And this also found the foundation of science. Science is not a collection of facts. It's always updating your belief and also admitting that your models is always imperfect in order to make like progress, right? So this is the philosophy behind that. The math is very simple, right? So this is why it's very like amused that when people say, I do my research in Bayesian statistics, right? Yeah, that, right? That is, right? But even Thomas Bayes himself think that this is such a tautology that why would I even write it down? So he didn't write it down, right? He just like put that in a manuscript and just like, okay, until he died. And then his friend like went through the manuscript and said, oh my God, this is amazing. This is the best K-pop, right? And then he published like this theorem. It's not about the math, but rather the deep understanding of how you should model the universe if you only have like a limited observation. And with this in mind, if you know that the data and WU should be on the same footing, means that they are just the X and Y that we just like mentioned, you can manipulate both of them as a random like variable. So this means that the Px given Y equals to Py given X times Px divided by Py. So if you try to understand each of these terms, all of this has very profound like meaning. So what is this, the one on the left? The one on the left say, given that I have observed the data, what is my belief of the models? So this is what we call the posterior, meaning that I do not know if the Earth is the center of the solar system or the sun is the center of the solar system. But once I see the sun rise from the east, can I update my belief on the models, right? So this is sort of the allegory of the cave, like dated back from Plato. So from Plato to Bayesian to Bayes to the thinking now, there is a very airtight, like the logical why this is so profound. But what Thomas Bayes say, once you admit that the model is the same as the data, they are both like random or variable, then you can update this term, provided that like you know the term on the right. Luckily, we do know how to do things on the right. Now, on the left is what we try to do. We would not have access to that. But the right-hand side here say, assuming that the sun is the center of the solar system, what is the chances that I will observe the Earth, the sun rise from the east, right? So that is something that I can do, meaning that I will make different assumptions of the models and try to match the data. But with one catch, right? Because if you treat things as a random variable, then you also need to admit that you need to make some assumption on the models beforehand. This is sort of like the limitation of Bayesian statistics, but what else will you do? Because you cannot do frequent tests, right? There's no way you can repeat the experiment. So this term say, if I do not know the data, what is my prior belief on the models, right? So each of these terms has their own like meaning. It's very like intuitive. The bottom part, like no one cares, is called the evidence. We will not care about that in this lecture, partly because it's independent of the models. You're marginalized over the models. In some cases, it's important, but for these courses, because it's independent of the models, we will just drop it. If this seems a bit too high level, you can think about the following like the cases, right? How do you estimate the price of a car in Canberra? You need two things. One is that what is the prior? What is the range of prices that like you think people here can afford? But you can also model, given any prices, what is the car that I can buy? This is something that I can like models. If you put all of this in XY plane, then I can start to ask, given Y, what is axis? And this is very important, right? So what they say is that there's really no ground truth. Your data is the same as the models. They all live in a random a variable space. They are just in this 2D XY plane. You can get P y given X as long as you know how to model P X given Y. Because, again, you're putting the model itself as the same footing as the data. And this is sort of the key that you should keep in mind about Bayesian statistics. Why this is important? So the goal here is define a likelihood, right? So we move on to one of the specific case of machine learning called the linear regression, i.e. like fitting a line. You might say, well, why do I want to fit a line? Like, isn't that like super dumb? No. So there are a few reasons why like fitting a line is very like powerful. So first is because Occam like razor, because if you want to build some insights of the system, just like the M sigma a relation, it's good to make sure that you're using a simpler like models, because that will lead to interpretability. Also, it's actually, as we will see, the beauty of linear regression is because you have exact solution. Not only you have like exact like solution, you also have what we call, you understand the statistical behavior. What do I mean by that? So take it in the lens of Bayes statistics, you need to admit that when you fit a line, you do not know the line because you do not have infinite like data. Your line itself is uncertain. The question is, can I actually know the uncertainty of the line? And for many algorithms in machine learning, you can do that. You can sample the posterior, but it's very expensive. But for linear model, you can do that completely analytically. So you can save time. And this is why, even though I make jokes that like 90% of the people in industry use like a linear regression, it's partly because sometimes when things are time or like sensitive, that's the only thing that you could do. You have the analytic resolution, you also know the posterior. As we will see why this is the case. One of the criticism is that, well, right, this is dumb. You're fitting a line. Turns out that you do not need to fit the line because you can always transmute your features into another space. Meaning that if I want to fit a models about the price of the real estate here, I do not need to exactly use the size of the houses. I can use the size square. I can use the size times the lot size. I can use the size times the year of the build. You can cook up arbitrarily numbers of features based on your input. Yes, you still need to cook up some features, but it does not matter because you always have the analytic solution. No matter what you do here, you can expand from 10 a dimension to 1,000 a dimension. It should not scare you because you know exactly the solution. There's no room for error. And you can do very like flexible feature and engineering. So the joke is, when I have dinner with my friends, they say that I only do two things to make, like 100, no, I'm not sure what his salary. You say, I do two things. One is a linear algebra and linear regression, and second thing is feature and feature engineering, which is fine because we'll see why this is the case. Take the example. So we talk about the M sigma relation, but let's say another cases where linear regression is very important. So this is called the KS law, the Kennicutt-Smith law. Not this Smith, another Smith, but yeah, Smith. So in Kennicutt-Smith law, it says that the surface density of the star formation rate actually scale with the surface of the molecular mass, which is quite reasonable because the more molecular gas you have, the more star formation you have. With a catch, because it's not in the linear scale, right? So this is actually in log scale. So this actually follow a power law, which is a lot of thing in astronomy. Luckily, even though this is not a linear relation, like if you take a lot of them, it becomes the linear relation. So this is an example where things are not linear in the feature space, but in the input space, but you can cook up the features that it will satisfy the linear relation. So for any composite of power law, this is always true. You can really see this is already very expressive, because many things can be written as a composite of the power law. And why this is the case, look at your assignment tree, the problem 1, why the wealth of the people follow a power law. There is a reason why power law and normal distribution is so prevalent in astronomy, as long as you have a hierarchical build similar to the wealth of the human, right? Not sure it's fair, but yeah, anyway. So what is the problem setting? So the problem setting in linear regression, just say, I assume my output y, a scalar, can be written as the linear composition of the feature of x. So I do not need to take x. I can take the feature of x, phi of x, like taking the log of x. And the assumption that I make is that in that space, I can find a linear combination that will lead to my production of y. And for notation convenience, because we like think about the simple case 1ax plus b, it's very clumsy to write the b, so we often extend the features with a constant 1. So you can write down this term exactly as a product of the two vectors, your features like vectors, as well as the weights, which is symbolizing the models. Okay, I will stop here a little bit. Do you have any question? Things will get really messy really fast. Okay, fantastic. So as I mentioned, well, we know that is the models, but how do you optimize the models? You can do a lot of like ad hoc things, but as I mentioned, I want to start with the concrete basis of the Bayesian inference. Anything that you need to know in any statistic, there's only one objective function, which is maximizing the likelihood. I try to build a model that maximizing the chances that I observe what I observe. So understand this, then you can ask, what is the likelihood of this thing, right? So for simplicity, we will assume that the data have some homogeneous noise, meaning that I do not know what my best model is, but my predictor, so X is what I observe, T is also what I observe. So I observe some training data, X and T. The chances that I will observe X and T, assuming the models, because as I mentioned, the likelihood say is the P of data given the models, assuming that I know the models, the chances that I will observe T is following a Gaussian distribution, because my observation has noise. So I would not expect that to fall exactly on the line because of the scatter. So for notation wise, we will just use this notation. The Gaussian distribution is given X, you have a mean and a variance. And the likelihood is just say for any single observation, X and T, the chances that I will observe T given X, given the models, is I will use the model to predict the mean, and then combine with the noise and compare that with the observation. I hope this is clear, right? This is, once you understand this point, then the rest is just algebra. Okay, thumbs up. Okay, one thumbs up, good. So there's only one data point, right? So you say, if I have n data point, what do I do? So one assumption is that if all my data point is independent, then observing all the data point, just like if I want to ask what is the chances that I have eaten a McDonald's versus it rained, if that's independent, then it would be the product of I have eaten the McDonald's, which I did, times it rains, right? So if I have n data point, then the combined likelihood is just the product of all the likelihoods for individual xn and tn. And this is a very nasty looking thing because you have the product of something. Luckily, this is a likelihood, a distribution. So this is all positive numbers. in fact, I think like a negative number is fine, because now you take the log. Log is a monotonic function, so it will not change the optimal point. So I can say, if I want to optimize my models, the WU of this term is equivalent of optimizing the log of this term, which is nice. If I take the log, then the log of the product equals to the sum of the log. I push that in. Now I just express this out, the definition of a Gaussian, right? Remember, I do not know the model. So I say that if I know what is the WU, then I know my T of n should satisfy the Gaussian, the distribution scattered by the noise. This is nice because it's log of some terms. You can break it, log A times B equals to log A plus log B. When log of the exponential becomes simpler. So if you do some massaging, then you get to these terms. And now you recognize something. All of this term, like do not these terms that depends on the WU. Okay. Sorry. That's got to the then you can close the door. So the WU here, if I want to optimize this term, then I can just optimize this term, right? So if I want to optimize my likelihood, is equivalent to optimizing these terms. And what is these terms? This is your chi-square, right? So if I want to say, how would I best fit a models with a homogeneous noise, is the equivalent of optimizing EW here, which is your chi-square. And this is even like nicer than you done. First, you have like recover like chi-square, the God-given a chi-square is just your likelihood. Even nicer than that, right? So like remember, if you have this term is a quadratic function with respect to the WU. So if you have a quadratic function, it looks like this, right? And then you have just like one optimal point, which means that if I want to find this point, I can just find the point that the differentiation of this is 0. As it's only one point. If I can find that point, it's the optimal point. Right, so I can write down this is equal to your complete square in high school, but just in a vector forms. So I can write down this as this is x squared. If I so here I use some very compact notation. Oh, actually this is wrong. This is sum of n's. Sorry, so there should be a sum of n here, which I completely missed. Yeah, so this should be a sum of n. Yeah, we'll change that. So, but by the way, I will always update the lecture notes after the lecture, because I always find typos because I'm not ChatGPT. So I will make a mistake. Okay, so you can write down in a very compact form. So you have n data point. You can combine all your features in a matrix that we call the design matrix, because individual row here dot with the WU should give you a scalar, which you should compare with one of the T. So if you write down all the files in row forms, then the matrix, the product, will give you the same expression as a summing up over n's here. This is nice. This is then you go back to your high school, remember how to differentiate with a quadratic function. You differentiate this, you get to these terms, rearranging the matrices, you get to these terms. So now you get the maximum likelihood or solution just purely based on the design matrix, which you can just populate this, right? So for any data, if you know what file you want to cook up with, this is for free. The matrix multiplication is an n square operation that is for free. The only very expensive part is this term. You have an inverse term. But look at this matrix, right? So this is a n times m matrices. You could have like a million data points here. That's n. Your features is going to be finite because your hands start to sore when you try to type up too many features. You don't it's very rarely that you come up with a very long features. So even you come up with a 100 dimensional like features, the phi transpose phi here is a m times m matrices. So this is a very cheap operation, right? Because the inverse of a featured a dimension times feature of a dimension is extremely cheap. And this comes back to one of the key points. The linear regression is absolutely dumb, but it's not, because the things that if you can come up with nice feature, it can really be extremely expressive, but you still get the exact the solution with exactly one line of like a NumPy, right? So you're using more than one line, then you're doing things wrong, right? That's great, but it's more beautiful than that. So in this term, we always assume that if we know the homogeneous noise, then I can solve for the WU. But I do not even need to assume that. I can say, I don't even know what is my noise terms is. I just say I have some intrinsic noise. As long as they are homogeneous, that's fine. Because I cannot make them non-homogeneous. If I have like non-homogeneous, then I have equally many a dimension as the number of observations, so I cannot constrain them. But if I assume that all the data have some intrinsic noise that I have somehow forget to measure, right? Somehow your theory is doing an observation. Somehow you forget to get a noise. You do not need to worry, because this is still the term that you want to optimize. Just that now you have two parameters, the WU and the beta. And now I can also do the same thing, like differentiate with the beta terms. This is also a nice term. It's a log is a monotonic function. This is a linear function. A monotonic minus a linear function is still convex. In fact, you can just show that if I differentiate this with respect to beta, this gives you 1 over beta. This beta drops. Then you can just say 1 over beta is equals to this term, will give you the 0 point, which is what is showing you here. And this is also very intuitive, right? So if I want to ask what is my intrinsic noise of the data, that is equals to the mean of the quadratic square, right? The mean of the square arrow. So many people do that for intuitively, right? So you say, oh, intuitively this should be true. But all of this is just, if you can write down, only thing you need to know is maximizing the likelihood. Why do you need to maximize the likelihood? Because that dude say that, the Thomas dude say that, because you do not know the truth. Cool. Even nicer than that. So we say it doesn't matter, you can get the optimal point, but for astronomy, you still lose if you cannot characterize the uncertainty of the models. Nice thing about linear regression is that even the posterior is analytic. So not only I can give you the best fit line, I can tell you the uncertainty of the lines. Why? So far, we have just maximizing the likelihood, right? We're saying that this term, maximizing the likelihood, which is equivalent of saying that I drop the prior terms, meaning that if I have no prior knowledge of what the model could be, then to find the maximum point of my posterior is equal to just maximizing the likelihood. Because if this P of the W is independent of a W, then we can drop that. But you don't need to do that, right? So you can make assumption on what is the WU. So if you want to fully characterize the uncertainty of the linear regression, then I need to assume a prior form for the WU. You can do anything, right? You can assume that any form that you want. You will become more nasty. You might need, like in lecture 11B on sampling to do that. But if you assume that your prior itself is a Gaussian, then things become nice again, right? So if I say for the sake of argument, I will assume that my prior of the weights follow a Gaussian, meaning that I do not know what is my slope is, but I believe that my slope is not too far off from M0 with some variance of S0. This is a very general statement. You can push S0 to be infinitely wide. It will just become the same case as maximum likelihood. But if I make this assumption, so what happens? So now my px given y is proportional to py given x times px. I already know my likelihood is the product of some Gaussian. In fact, I can write this down in a very clear form as a Gaussian. And then my prior, if I assume that to be a Gaussian, then I have the product of two Gaussian. Like Gaussian is very nice, right? The reason is because you can do a lot of manipulation with Gaussian. So you can ask, what happens if I product two Gaussian? So if I want to get the posterior, then I want to do the product of two Gaussian. If you write it down in the scalar form, remember if I have exponential minus x squared divided by 2a times exponential x squared divided by 2b, I can combine the things in the exponent. And then you complete the square, yada, yada, right, in high school. There's exactly the same form in the matrix form, which I will not prove. It's a few lines of code. Either ask ChatGPT to prove for you, or you can believe what I say is correct. This is very simple. Like even you go to Stack Overflow, it's like 5 lines of proof. So if I assume P of X is a Gaussian and Py of X is also a Gaussian, then Px given Y is also a Gaussian with exactly the formula that you know. Not only that, you can write down the variance, the mean, and the variance of the posterior. So now it's just like plugging in things, right? So I know already what is P of X, which is my prior terms. So I assume that the prior has a mean of M0, a covariances of S0. I know that is a linear model, so I have AX times B, where A is a design matrix, and I have the noise to be a homogeneous noise. Seems a bit daunting, but if you sit down for like 5 seconds and just write it down, it will become clear. Nice thing is that now you can get the covariances of the posterior. Not only that, you can also get the mean of the posterior. What does that mean? Right? To recap, what does all this math say? This is a lot of math, but what does this mean? Meaning that if I want to fit a line to the data x and t, I want to ask what is the best WU. I do not only know the best WU, I also know the distribution of the WU. So I know the posterior of the WU. What does that mean? Right. So exactly the form here. Let me skip through the plot first. I think it will make sense. Here, right? So what this means is that if I have some data x and y, I want to fit a line, there's not one line that can fit that because I do not have infinite observation. Like remember, Bayes say we cannot do that frequencies. We only have like 3 data points. There will be, given that the data point itself has noise, then there are lots of different lines that could fit the data equally well. What you really want is the distribution of the slopes and the intercepts. And what the formula here say is that you know exactly the distribution of the slope and the intercepts with analytic like a solution. This is like, take a second, take a deep breath. This is how you get 90% of the industry job done. You code up the features, put that in a design like matrix, then you go to your boss and say, not only I can give you the best price estimate, I can give you the uncertainty of the price of the estimate with 1 line of Python. And then your boss is like so impressed, and then you get like the promotion and then yada yada, right? Of course, this is a very generic case. So what if, let's simplify this. So we say that the prior itself is with some mean M0 and S0. Let's take a simpler prior. Let's say the mean is 0 and the width is isotropic. What this prior means is just that I really try not to fit a line. I assume that there's no trend, right? So I just say a priori, the prediction of y should not depend on x. So I have a slope of 0. This is my prior belief. And I have some confidence of my prior belief that is characterizing by the eta square. If I now plug in this, then you can get to this formula, which is pretty neat. All right, so let me show you what does that mean. So you get that if we make this particular assumption of the prior, then the mean of the posterior and also the covariances of the posterior are known. If my sigma is very small or my eta is very big, then these terms drop. If this term drop, what I get back is phi transpose times 5 inverse phi transpose t. This will bring me back some memory. So I remember when I do some interview for some quantitative firms, the first question they ask is like, what is the analytic solution of a linear regression? So if you cannot instantly say phi transpose phi inverse times phi transpose t, then you're out, right? So that's the very obvious thing. But this is interesting. If I have infinitely broad prior, meaning that I really have no constraint on all the models, then I go back to the maximum likelihood case. Or if I have very strong belief of my data, then it does not matter what is my prior. Then I also go back to the maximum likelihood case. Yeah, so this is just the maximum likelihood in some limit. Again, I should emphasize enough. All this happens because we believe that the model itself is uncertain. And we want to quantify the uncertainty of the models as well as the data, right? So also that what's Bayes say, there's a bonus. Remember, if I say the posterior is equals to the likelihood times the prior, if I take the log of them, I will get the log of the posterior equals to the log of the likelihood plus the logs of the prior. If I assume that the prior is isotropic, then I can write down this term, right? This is the exponential of the minus eta w squared divided by 2 eta squared. So log of this will become these terms. And the likelihood is just what we have written down, the chi-square. This term might look familiar to some of you, right? So sometimes when you do a machine learning fitting, like your neural network 101, you would say, how do I make sure that I do not overfit my data? One of the tricks is to say, I will include a penalty term. And the penalty term, I can take what we call the L2 regularization. Meaning, what does that mean? Meaning that if I think about this as a polynomial, I really encourage things to have zero coefficient. Because whenever I have a non-zero coefficient, I have include a penalty. So meaning that I only use the term that I really need when I really need it, when it really have some belief that this is helping to fit the data. This is controlled by the term over 1 over 2 eta, meaning that how strong your belief is, how much you want to regularize your data. And this really sees some form where a lot of things that we just take for granted, we do the regularization. It really comes from the fact that it's equivalent in the Bayesian lens, like trying to include a prior belief. And that will regularize your models. What does that mean? If I want to fit a polynomial, if I include the regularization terms, I can force that to be using fewer coefficient to make it more rigid. So Bayesian wheel of the linear regression give you a sense of how you would tune the rigidity and the flexibility. And this is nice because I say that the linear regression can still be extremely rich. You can cook up as many features as you want, but you might be worried that if I cook up 10,000 features, how do I control them? I might overfit. Luckily, you can still control them through the regularization terms in the context of the prior of the distribution. One more thing, right? So now I only give the Oh, by the way, just go back to why the posterior is important. Think about your M sigma, the KS law. If you go to your advisor and say, I believe the KS law have a slope of like minus 1.5, your advisor will be not pleased. If you say, I know that my slope is minus 1.5 plus or minus 0.21, your advisor will be very impressed because now you actually know what is the uncertainty of the slope based on the data. Right? And this is important because in many cases in astronomy, we care about the parameters, but some cases we care more than just the parameters. So, lots of math, lots of math, amazing, matrices. Okay, so sometimes we want the WU, which is what we are after. But sometimes we want more than that. So what is more than that? Sometimes we want to say, after I have fit the models, can I predict for a new like input? Can I predict what is my new output? That is a catch, right? If you fit the maximum likelihood, then you would say, I have the best fit models. I will use the best fit like models to predict my next data point. But remember, in the base like version, the models itself is uncertain. So you need to marginalize over the uncertainty of the models. Or in the simplest case, you can run like simulation, meaning that I have a bunch of lines. Each line will give me a different Y star given X star. I can just run that. But you can also do that analytically. So what do I mean? As I mentioned, for the data point, you have fit like a different line. So now you say, if I have a new data point X star, can I predict what is Y star? But that is a U-defined question because my model is uncertain. So I need to make sure that I can say, for different like models of my posterior, what would be the Y star? Think about the M sigma relation. You do not just want the best infer black hole mass. You want to say, given the input of the classical bulge, what is the distribution of the black hole mass? In many cases, this is a very expensive operation, but in linear like algebra, this is one line, right? Why? Because turn out that, again, the Gaussian save the day. If you have two Gaussian, multiply them and integrate like over them, turn out that it's still a Gaussian. And this is why like Gaussian is so amazing. Like people have not appreciated like how amazing the Gaussian is. It's very, very like practical. So turns out that if I have Px given y is a Gaussian, Py given x is a Gaussian. If I multiply them and integrate over them, this is still a Gaussian with exactly the formula that you can ask ChatGPT why like how you derive this. And now you just plug in some numbers, right? So all this number we know, and then you get the posterior of your new x given y. I will use the last 10 minutes to say why this is like important with a tutorial. So congratulations, you have finished the easiest part of the courses. So we have talked about the supervised and unsupervised learning. Yeah, yes and no. Actually, this part is pretty tough, to be honest, because if you have not like familiar with the Bayesian like inference, but so I think the concept is important. So once you get the concept, I think the rest is just quite mechanical. Like hopefully, you can just like go through all the plugging in, or like yourself. We talk about some jargon in machine learning today. We started like really high. We just say, let's do like everything in the Bayesian like context. So we waste no time. We do not need to say, oh, if you see this, you also have the Bayesian. Let's just go like Bayesian, which is why like it might be slightly more daunting. We start with the linear algebra. Hopefully you have appreciated how rich the linear regression is. It literally can solve almost like a lot of the question, not only in industry, but also in astronomy. Why this is so rich? Because it's very flexible. You can cook up like features as many as you want. All the solution, not only the maximum likelihood of solution is analytic, the posterior of the model is analytic. And even when you ask, given a new data point X, what is the output Y, is also an analytic. I know this is like a bit daunting but I want to show you why this is so powerful. And this is unfortunately because this first lecture there are more material about all the jargon, so I might not have time to do the live coding, but I will walk you through the concept of this Jupyter notebooks. So this is a very classical like problems, turned out to be very beautiful. Good and bad things are like there are lots of like paper being like written in the same domain, but they often call like different names. But they're actually in the context of linear like regression. So so what we are starting here is to say, assuming I have some spectra, right? My spectra is my X. I want to infer some labels. So the label can be the temperature of the star, which is what we try to infer here. So you have some input spectrum X. X is very high dimensional, but who cares? Because it's linear like regression. Like everything is analytic. I have 7,000 pixels. Who cares? It is like it. And then we try to infer the output Y, which is assumed to be the temperature. And how would you infer the output Y? We started with just splitting the training and the test set to make sure that we are doing a fair comparisons. And we say, let's say I have a subset of stars that I know the ground truth or the temperature. Can I infer for the other spectra what are the temperature? Let's forget about the prior terms. The maximum likelihood solution is analytic. So you write exactly one line, then you get the best fit like models, like literally one line, no packages, like beside NumPy. And then you say, well, now if I have a new spectra, phi, I can predict what is my temperature, right? Exactly one line. And then you say, wow, you see, I can get the temperature of the star. And it's between 130 Kelvin. And for people who have worked with spectra of star, then you appreciate this, how important this is, because there are lots of pipeline being built to get down to like 50 like Kelvin. But with 2 lines of code, we get to about 130 like Kelvin, right? And you can do better, as I mentioned, because we're using a lot of the feature. So the X is very high dimensional. So you might risk of overfitting. So I can include the regularization terms. Where does it come from? In the Bayesian context, it's come from the prior terms. Luckily, even with that, the solution of the best fit models is also analytic. Again, with 1 line of code, and then 1 line. Oh, so now you loop over because that you do not know what is the lambda. But of course, like making a matrix multiplication like 10 times take no time. So I will loop over like different lambda and plot what is the best loss as a function of lambda. And then I find the best loss, and this gets me to about 100 like Kelvin. So with 1 more term, we shave down another 30 Kelvin. You say, well, I don't like this because I'm only using X as my features. My teacher tell me that I can cook up more features. Yes, you can. So now for any X, I will also cook up X squared. So instead of n pixel features, I have 2 n pixel like features. Who cares? It's 2 times the matrix. Again, 1 line. There are more lines to calculate the error than like solving, which is super annoying, right? So 1 line. And then now we shave down things to about 90 Kelvin. And then there's a bonus. So we are only like in the best fit model. You say, well, I really want to know, given a new spectrum, can I know my uncertainty of the temperature? Can I just not just get the best fit models? Can I actually estimate, given any new X's, what is the distribution of Y star? Turns out that this is also 1 line. There's a lot of like 1-liner, right? So here you can do 1 line. And then not only you can predict the temperature, so this is the truth like temperature versus the predicted one. You also have the arrow bar. Most of that do follow quite well, meaning that the arrow bar in 1 sigma do fall into the like the scatter. Some of that is outlier, which is not surprising because your model itself the relation between the temperature and the spectra is not exactly a linear relation. So some of that will under estimating your error because your assumption of the models is not like correct. But in many cases, you get that pretty like correctly. So hopefully you can appreciate this. I think like this is really, if you understand this, you can probably leave the classroom and you should be happy because you can do a lot of like research already. And this should always be your first line of approach, right? So think about like anything that you want to do, either for regression, you do not need to spend 3 months to see if your pipeline is working or not. There should always be a one-liner that you can check whether or not your project have like potential, because you can code out the feature, you can code out the uncertainty. So here is the linear regression. Next week, we will start with classification, but in the linear regime, in the Bayesian regime. And then, yep, if you have any questions, feel free. Yep, I will stop here. Okay.